is Jason Hartline. We're very much looking forward to your talk.
All right, thank you. Yeah, so this paper is in a space that I think David, in his introduction yesterday, motivated very well, which is if we're designing mechanisms in an environment with lots of data, we're going to have to start thinking about how to bring econometric techniques for inferring sort of preferences inside the mechanism design problem. This is in joint work with PhD student Alec Johnson, who's finishing up and on the postdoc market this year. So if you're looking for someone with expertise in that area, he's fantastic. Dennis DeCapella, who's an econometrician at University of Virginia, and Ono Zuder, who is the head of data science at Booking.com. We were all visiting Booking.com in Amsterdam for 2 months in the summer 3 years ago, where a lot of these questions were initially posed, and we started thinking about them. Cool. So this paper is on dashboard mechanisms for online marketplaces. So they're broadly two categories of market design I think are really quite different in terms of the methods that you're going to be thinking about to think about them. There are the very infrequent markets like school choice, spectrum auctions, where you look for certain kinds of market mechanisms. And then there are the very frequent, million times a day markets like ad auctions, like Uber, like Booking.com, where you have agents interacting with these things that are allocating stuff basically in real time continuously. So this talk is focused on the latter kind of market. Okay, so online marketplaces and dashboard mechanisms. What I mean by that is this idea that the mechanism maybe should be communicating to the agents something about what's going on in the marketplace to help the agents make better decisions. Okay, that communication is often a bidding dashboard that the agents have for seeing, maybe what happens, counterfactual estimations of what would happen for different strategies they might take in the marketplace. And so here is in the background of this image is an example dashboard that was on Booking.com a few years back, where as a function of the commission that you might be paying, it shows you how much your visibility on the booking site might increase. Cool. So my interest is generally in online marketplaces and how to make online marketplaces function better. Okay, so what I envision with online marketplaces is the following scenario. There are a bunch of short-lived users, and they are matched by the marketplace with strategic long-lived agents. So again, users might be users on Google and the agents are advertisers, or users might be people searching for a hotel room on Booking.com and the agents might be the hotels. Okay, there's some matching algorithm that prioritizes the agents in some way, and then the users show up and make a decision about who they're going to match with. Okay, so there are a bunch of examples of these that are quite relevant. I want to make all of these things work better, so I don't really think about any one of them in particular. I want to motivate what I'm thinking about in the following perspective. So comparing algorithm design and mechanism design. So algorithm design, something we've studied in computer science a lot in the last half century. Given input values, determine a good output, and our goal is to optimize some objective like welfare. Mechanism design contrasts with this because we allow the fact that the input might be strategic and the agents might manipulate the input to the mechanism to try to get a better outcome. And so we'd like to determine an outcome that has good welfare and come up with a mechanism that has good outcome in equilibrium when everyone behaves strategically. Okay. Amazingly, there's a very popular reduction from mechanism design to algorithm design. It's the VCG mechanism in some scenarios, or more generally, there's unbiased payment mechanisms or implicit payment mechanisms. Essentially, at a very high level, what these do is they carefully construct truthful payments to incentivize everyone to just reveal their true preferences. Okay? And here's the problem. online markets don't look like this. Online markets do not have truthful payment formats. And you're just not going to be allowed to design online marketplaces with these because it gets in the way of many practical concerns in these markets, or maybe even issues of credibility that Shengmu was talking about yesterday. Okay, so I'm not going to care why we don't have truthful mechanisms in online marketplaces. I'm just going to assume we don't have truthful mechanisms in online marketplaces and see how are we going to design mechanisms in this world where we aren't allowed to design truthful mechanisms. Okay, and one of the issues with sort of the theory on this is that this truthful idea is so compelling for theorists that most of our literature is stuck there. And we haven't spent enough time thinking about how to do things in this world. Okay, so this paper and some other papers I've written recently are part of what I hope to be a really fascinating research area that looks at how to design non-truthful mechanisms. Cool, so here is an example of what I'm going to be thinking about. Winner pays bid format mechanisms. These generalize the first price auction that Shengmu was talking about yesterday. The basic idea is we're going to ask for bids. We're going to take the bids and map those to who wins. And then in the end of the day, the winners are going to pay their bids. Okay, so in these winner pays bid format mechanisms, there's only one place where you would, as an optimizer, get to change things, and that is in step 2. Okay, step 2, you can decide to map bids to who wins however you wish. Okay, and the question is what are good ways of mapping bids to who wins? Okay, a very classic way is the highest bid wins mechanism, or for a single item, it would be at the first price auction, but you could imagine this more generally. Allocate to the feasible set of agents to maximize the highest total bid. Okay, if I was selling one item to 2 agents, a highest bid wins, winner pays bid mechanism is the first price auction that Shengmu was talking about. I have a simple example here. I'm not going to talk about it in detail, but essentially, if you have bidders with some values, they're going to strategize and bid. Essentially, in a full information environment, they're just going to bid basically the second highest bid, but the highest bidder bids slightly more and wins, and that's going to be actually pretty close to optimal. What I want to point out, though, is that if you were to change this environment to make it more complex, so this was selling one exclusive ad on, say, any of your favorite search engines. But you can imagine a situation where you could sell either an exclusive ad or you could sell a shared ad space where you show more than one advertiser at once. You have to choose, sell one ad or sell 3 ads. That could be something you had. And so I could basically take my same example before, these 2 agents who want the exclusive ad, but I'm going to add also 3 agents who want to share the space. Okay, and in fact, the equilibrium I had before is still an equilibrium here where these new bidders just pay 0, a bid 0. And now we're getting the same welfare as before of 110, but the optimal welfare was 200, about 300, right? In this new equilibrium. And so you see from this example that not thinking about how to design winner pays bid mechanisms can result in winner pays bid mechanisms that have really awful equilibrium, off by a factor of 3 here. Obviously, you can construct even worse examples if you want. Okay, so my question is, how do I choose the algorithm in step 2 so I don't get bad outcomes like this in equilibrium? Cool. So there are actually 2 challenges that I think are the big challenges for winner pays bid or non-truthful mechanisms. One challenge is that the agent strategies themselves are non-trivial. If I was told you bidding in this scenario, come up with a bid, you'd be like, I don't know how to do that. Okay? The other challenge is that equilibrium can be very bad. So I'm going to be proposing solutions today that are going to address both of these challenges. Okay? My solution is bidding dashboards. Okay, I'm going to publish a dashboard which attempts to give the agents counterfactual information about what would happen for every bid they might put in the auction. That makes bidding easy. You just optimize for the dashboard. Okay, I'm then going to think, okay, if we're designing dashboards, maybe that might change how we think about designing the mechanism. because we have given them a dashboard, and if they're responding to it, well, that might help us in some way. So I'm going to then be thinking about how should I be designing this market mechanism that is aware of the fact that I'm giving the agents a dashboard and they're responding to it. Okay, the main questions I want to address here: what dashboard do I want? What mechanism do I want?
And the product is homogeneous. It's always the same product.
I'm imagining I have these long-lived agents that are bidding every second in this market mechanism. Maybe things are evolving over time, but that'll be a detail I'll talk about in the future.
But at a given time, there's one good. It's just different.
Again, so think about the setting of hotels or advertisers matching to users. So at a given time, there's one user shows up. Who do I match the user to?
Right, but the rooms are identical.
The agents are the hotels, and the user's matching to the hotel rooms with some preferences of the user. The hotels are not identical, but the agents are the hotels. Okay? The user is being allocated to the hotel in some way. Okay, and to all the hotels, the user today is a different user from tomorrow, maybe, and some user might be a business user or whatever, but it's not going to be important for the discussion. Cool. So I'm going to answer the second question first. I'm going to tell you exactly the dashboard mechanism I have in mind. It's very similar to ideas that were mentioned in some of the past talks, Sheng-Lu's talk, for example. But I'm going to do what he said not to do, sort of. So I'm going to publish a dashboard, which is my estimate of how we're going to map bids to the likelihood of winning. I'm then going to ask for bids, and then I'm going to assume that the bidders have actually responded to the dashboard I published. Okay? If they've actually responded to the dashboard I published, then I can really easily invert their action to get their preference. Okay? So I infer the values from the bids as best response to the dashboard, and now I'm in a great position because I know what their values are, and I would like to have my market be the most efficient possible. Okay, I'm not trying to maximize revenue. I want an efficient marketplace. And so I'm just going to run this desired allocation rule, which my engineers have given me, which is optimizing the total welfare on my platform. Okay, with the true values, not the bids. Okay, and of course, I'm required to use a winner pays bid mechanism, so the winners pay their bids. Okay. So here's a main question. I think I might answer your question, but let's take a second. So the main question is, this seems wrong. And maybe I'm going to get sued. So I'm going to change it a little bit and say, well, okay, in the first step, I was publishing a dashboard. Maybe my choice of dashboard has impact on whether this is a good approach or not. And so I'm going to ask the question differently and say, well, for what dashboards is this mechanism a good mechanism?
Sorry, it seems wrong because you might charge more than bids.
It seems wrong because I told them there was this dashboard, and then I went and did something that had nothing to do with the dashboard. I got their values, and I implemented the efficient outcome.
It's using the dashboard to infer the values. So.
Yeah, but so I publish what I'm going to do. You make a choice, and then you get something that may be different from what you thought your choice was giving you. That's why it seems wrong.
I was assuming the bid allocation rule is consistent with the mechanism. The dashboard is consistent with what's happening now.
Well, I have a chicken and egg problem, right? Because, think about the first day.
But in equilibrium it is.
So it's fairly easy to get an equilibrium result, but then you're worried about maybe getting to the equilibrium. But exactly.
Okay.
So
the
and things could be changing over time, in which case maybe it's never right. Is that a question? Still?
My question was related to this, what is binding about the dashboard?
Exactly. So this is the main point of the entire talk. So we're going to be addressing what is binding about the dashboard. Yeah. Okay, so to give you some overview, I'm going to tell you how to construct dashboards. I'm going to give you several designs of dashboards. I'm going to give you dashboards with increasing good properties. Okay. For the first result, it's going to be David Parks's result. It's going to be in static environments with static values that following the dashboard converges to an equilibrium. Okay. And then I'm going to give you a more sophisticated dashboard that has a stronger property in dynamic environments, but if you have a static value, you want to follow the dashboard. So even if things are changing underneath you, you still want to follow the dashboard. Okay. Following the dashboard outcome converges to what would have happened for you if you'd run the sequential truthful mechanism instead.
Sorry, did you define a dashboard yet?
A dashboard is a counterfactual estimation of what might happen for you for various bids you could place, but I'm going to formally define it on the next slide. So if you want a mathematical definition, it's coming. Okay? And then my strongest result is in dynamic environments with dynamic values. The dashboard mechanism was going to be approximately strategically equivalent to running the sequential truthful mechanism with the same allocation algorithm that the engineers gave me. Okay, so my engineers give me an allocation algorithm. I'm going to assume it's monotone, meaning the higher value an advertiser has, the higher probability the agent will get served. And we all know that there's truthful payments that go along with this allocation rule. And so the outcome of my dashboards, the dashboard is going to be basically strategically equivalent to the truthful mechanism. And following the dashboard, meaning bidding your best response for your value in the dashboard, is going to be corresponding to the truth-telling strategy in the sequential truthful mechanism. Yes?
You still assume commitment by the sort of designer in the sense that I as an agent know exactly what you do for any sort of bids that are made after the dashboard and how you allocate based on that, right?
You're asking about commitment.
The usual, you commit to what you do with all the bids that are made after the dashboard.
Yeah, so here's my philosophy on commitment. I'm in a repeated environment, okay? And if we're interacting and I keep saying the wrong thing and you keep not getting good payoff, you're just going to leave.
That's the way I should think of the mechanism. As sort of, that's what agents just know is going to happen. For any bid profile, they know what the mechanism does.
It's not important. It's not going to be important. That's actually a strong result. So this sequential truthful mechanism has ex post Nash of being truthful, right? Sequential truthful mechanism. And so you don't have to actually know what's going to happen in the sequential truthful mechanism, and neither will you have to know in my dashboard mechanism. So the environment could be changing under you, and you might not know it. Okay, so here is my outline. I've given you some motivation. I'm going to spend some time talking about single agent mechanisms, which are way easier than multiple agent mechanisms for designing winner pays bid mechanisms for. I'm then going to give you my dashboard constructions and some of the analyses. We'll see how much time I have. And the last thing, which I am going to guess I'm not going to have time for, is, and I'll then refer you to the paper, is what I call single call dashboard mechanisms. And this is the following difference, which is actually really important practically. In theory land, it's not so important. Here's the point. So in many online marketplaces, I only know what my engineer's algorithm is going to do by actually running it for live. Right? That's the only way I know what my algorithm does. Okay? And in particular, I don't know what the probability is an advertiser would have gotten a click, or the probability a hotel would have gotten the booking if they had put in a different bid. Because I didn't have that bid. I didn't try that. There's no way to do that without actually running it live. So the single call model is the model where I can only ever run have access to my algorithm by running it. Okay? And so the point is that all the dashboards I'm going to construct are going to be able to be also constructed in the single call model, which is, I think, the practical implementation of this.
I'm still having difficulty. Should I think of this as something that's in front of the car when I drive the dashboard, or what is the dashboard?
So it's these bidding dashboards that are in place in many of these mechanisms. It's It's like a console where the advertisers come and they see all the parameters they have to configure, and they also potentially get some feedback about what might happen when they change their bid or other parameters of their campaign.
They can see lots of people's bids and so on.
No, they do not get to see lots of people's bids. They see predictions of what might happen for various bids of theirs. Okay, cool. So I want to jump into the first topic, which is understanding single agent mechanisms. Okay, so I have a single agent with value v. A truthful mechanism is going to be defined by an allocation rule x and a payment rule p, where x maps v to the probability of winning and p maps v to the expected payment made by the agent. Okay, a winner pays bid mechanism, I'm going to put tildes on these to denote that. Has a bid allocation rule which maps bids, not values, to allocation probabilities, and bids, not values, to payments. For winner pays bid, that's easy because the payment with a given bid is just your bid times your probability of winning. Okay, so for winner pays bid mechanisms, I already told you what the payment rule is. Okay, I'll denote B as the strategy, calligraphic blue B as the strategy which maps values to bids. And then the revelation principle is pretty nice. It tells me that if I understand truthful mechanism, I also understand winner pays bid mechanisms because this x tilde, b tilde, p tilde can only be a non-truthful mechanism in equilibrium with bids b if, when I compose it with my allocation rule, I get a truthful mechanism that satisfies a truthful mechanism. Okay, and so now I can use the characterization of truthful equilibria to understand what's possible in this space. So a mechanism is truthful if and only if this x is monotonically non-decreasing and the payment rule satisfies this payment identity of Roger Myerson. Okay, this payment identity probably is not new for almost everybody here, but just to see a pictorial representation of it, if my allocation rule is this black increasing, non-decreasing line, okay, then v times x is the surplus, which is this red rectangle, v times the probability of winning. This minus this term here, that's the area underneath the curve, right? I integrate, I get the area underneath the curve. Okay, that turns out to be the utility the agent gets because the payments are equal to the surplus minus this utility. That's what the designer gets in terms of payments, the area above the curve. Okay, so that's the picture you should have in your mind about this characterization. And basically what I'm saying is, if I tell you my probability of winning, I'm also telling you the payment up to a P0 term, which is how much a player with value 0 pays.
So is the dashboard that curve?
So you can imagine the dashboard being this curve X, but if we're designing a winner pays bid mechanism, we ought to give the dashboard in bid space, not value space. So we'll give it translate into bid space, and so I'm about to do that. Okay, so cool. This is if I want to design a truthful mechanism. What if someone gave me, my engineers give me X, and they say, I want you to do this in value space, but you need to do this with a winner pays bid rule. Okay, so you need to ask for bids, map the bids to a probability of winning, and then if the person wins, they pay their bid. Okay, so that's actually also quite easy. So basically you can use the revenue equivalence idea to do this, and I'm basically going to do that right now. So cool, our payment had to be this for the truthful mechanism, but we know our payment in the winner pays bid mechanism is bid times probability of winning. Okay, so the expected payment divided by my probability of winning has to be equal to my bid, so I can solve for it with this formula. So if you tell me you want to implement this X, I can tell you, well, your strategy in the winner pays bid mechanism that implements that X has to be this bid function. And now, as long as this bid function is invertible, right, it's monotonic, then I can just invert it and put it into X. And so X tilde B, my winner pays bid rule, is just take my bid, invert it with the bid function I know has to be the only bid function that works here, right, and plug that into X, the engineer's allocation algorithm, and I get the thing I want. Okay. Interestingly, and I did not realize this for a long time, so when I'm implementing truthful mechanisms, I can have any P0 I want. For non-truthful mechanisms, actually, P0 can be at most 0. And the reason why is that this is not monotone if I have positive P0. And that's because, look at P0 over x of v. As this goes to 0, when you get small, this thing goes to infinity. And the guy with value going to 0 has to be bidding going to infinity, which obviously can't happen in the mechanism. Right? So actually, Meyerson's characterization can be refined for winner pays bid mechanisms to require P0 to be non-positive. That'll be important later. Remember that. Yes, question?
This relies on you, the mechanism designer, knowing the distribution of valuations.
No, there was no distribution here.
Well, but you are inverting the bids.
I have only one player,
Yeah.
and my engineers have given me the allocation rule, and I know the allocation rule for one player. And usually in mechanism design, that allocation rule comes from the distribution of other players. But for my one player example, I'm just assuming I have a fixed allocation rule. Good?
You have to invert the B, like,
I'm imagining my engineers, for some reason, didn't want to serve an agent with low value. So they gave me a one-agent mechanism with a probabilistic allocation rule. That's a strange thing. This is going to plug into my later analysis, where it'll come from other bidders. But for now, we don't have to even think about other bidders.
no, I'm not worried about that. I'm worried about how do you invert the bid function. Like, I don't see how to invert this crazy integral thing. Are you just gonna?
I mean, it's a monotonic function. I mean, do it numerically.
Numerically? Okay.
So this is just like if you took a second price auction and used it to calculate the equilibrium bids in a first price auction.
Exactly. If you were solving for the bid strategy in a first price auction from the second price auction using random equivalence, you'd have done exactly this.
Sorry, so the assumption is that your bidders are optimizing. So they're actually playing the...
Yeah, I have one bidder. I have one bidder. This bidder has a value. I want the values to map to allocation probabilities by the rule my engineers gave me. Okay, but I'm required to charge winners their bids. So I have to come up with a new bid allocation rule, and this is exactly just how you do it.
Right, but the assumption is that that bidder is optimizing correctly.
Yes. Yes. So the point is, this is the right optimal strategy for the bidder when I correctly derive the mechanism x tilde. Okay, so this was the one bidder case. It's all super easy. Things get very difficult very quickly when I consider more bidders because I have x given in value space, and if values are now a profile, then I need to simultaneously solve for all the values so that when one player manipulates their value, I get the right curve and I get the right bid, and everything is going to sort of break in doing this directly for multiple bidders. So the big, essentially, if you want to, like from a theoretical point of view, you can view the work that we did in this paper as reducing the multi-bidder case to the single bidder analysis.
Can't use the interim allocation?
I am going to be designing mechanisms for Nash implementation, not Bayes Nash. And so there's full information on the part of the bidders. And so interim is not a thing in what I'm doing. Okay, dashboard construction and analysis. I'm going to go over some of the main ideas, and then we'll go into some more detail. Okay, again, it's a high level of what are the ideas that go into coming up with a good dashboard. Okay, so here's a good first idea. Use historical values as the values you're going to plug into the allocation rule to estimate the dashboard. That's a pretty good idea. If values are constant, that's going to be pretty reasonable. Okay. Then I can, as I said before, infer agents' values from the best response to the dashboard, and I can use these past inferred values in future estimated dashboards. Okay, I'm going to get from these first two bullets, following the dashboard is going to convert us to Nash, as David suggested. Another really helpful idea, and we'll see why, is actually, I should only update my dashboard when the agent wins. Okay, we'll see why that's a really good idea.
Can I ask you, the actual implementation, you have bits coming in from other agents, and if you're using the historical.
I'm going to give a very formal definition on the next slide. I'm going to give intuition for the main ideas that go into things, but I'll have a formal definition. Do you think waiting is going to be fine? Okay. So if I only update the dashboard when an agent is allocated, then the payments I'm going to assign are going to converge to the truthful payments for a static valued agent. Okay, so even if the environment is changing dynamically, the payments will converge. Okay, so it's much stronger than the Nash result. Okay, and then the last idea is if I want things to work with dynamic values and dynamic agents, the idea is, look, my dashboard might be wrong. I don't know what the future holds, so the dashboard might be wrong. Let's keep track of how much it's wrong, because we do know ex post how much it's wrong. Okay, and then I'm just going to keep track of how much I charge people incorrectly and give them a rebate in the future, and I can give them that rebate by adding that to the dashboard. I can add it essentially as adding it to the P0 term, right? Except that I can't really, as I showed you, I can only have a non-positive P0, and so I have to sort of do that a little bit more cleverly. Okay, and this last thing, bullet 4, this is a really popular idea in designing mechanism for repeated environments. Okay, this idea of linking decisions across rounds makes things a lot easier. So I'm going to link decisions across rounds. I'm going to keep track of how much my payments were wrong, and I'm going to guarantee I'm going to give that person that payment back. Okay? And this is going to give me approximate strategic equivalence to the sequential truthful mechanism. Cool, you guys have been demanding definitions. So here's my dynamic model. I have stages 1 through T. I'll have valuation profiles that could be different in every stage. So V sub I super S is player I's value in stage S. Okay? I have a stochastic allocation algorithm which is going to map, this is from the engineers, the profile of values to probabilities of winning. Okay? Inside this is the user's choice, which is why it's probably stochastic. So the user comes and maybe we model them randomly, so a random agent's going to win. Okay? The reason why this might change for the round is because different users in different rounds, and so they might make different choices. Okay? We have linear utilities. I'm requiring winner pays bid in each round. And I'm going to occasionally consider the static model, where I'm going to drop the super S's, superscript on S, because everything's going to be the same. Okay, values will be the same in every round, and the stage allocation will be the same in every round.
Jason?
Yeah?
The input to X is the bid profile or the value profile?
I'm sorry, what was the question?
The input to X, is it the bid profile or the value profile?
Yeah, so this is the allocation algorithm in value space that my engineers want. So I'm assuming my engineers found a good way to map values to who should win to optimize the platform. And my job is to design the bid allocation rule in bid space that has good properties with winner pays bid payment semantics.
So that's kind of what they want to implement.
Yeah. So again, if I don't have a tilde, it means it's in value space. If I do have a tilde, it's in bid space. Okay? So I would love to design this winner pays bid mechanism to single call implement the sequential choice, this basically as a sequential, the series of social choice rules. Cool. Now to formally define our dashboard. So our dashboard is going to basically be counter estimates of what would happen for any bid of the agent, what are they likely to get served. So this is a profile of bid allocation rules with one bid allocation rule for each agent. Okay, and agent I gets to see their bid allocation rule. Okay, I'm going to be talking about the algorithm that we're actually running and the dashboard we're showing, so it's going to be helpful to have different notation for those two. So the algorithm is going to be allocations, payments, bid allocation rules, and bid strategy. For the dashboard, it'll be allocations, payments, a bid allocation rule, bid strategy. Okay? We're always going to be running this, but we're going to be showing them this. Okay, so here's my dashboard mechanism. Formally, I wanted to find the bid allocation rule to map bids to who wins. I'm given some dashboard, and I'm given the stage allocation algorithm. Okay? Later, I'm going to be telling you how to construct the dashboard that I want to be given in this round so that good things happen. But for now, I'm given the dashboard. So I'm going to publish my dashboard and solicit bids. I'm then going to infer values using the inversion of the bid function for the dashboard. Okay? And I'm then going to just run my stage allocation algorithm the engineers gave me on the inferred values. And of course, charge people their bids. So if you win, you pay your bid.
So does the agent know that the algorithm and the dashboard might be different?
It's going to be readily apparent when they bid something and they get something else. But sure. I'm going to prove a result that says that following the dashboard is approximately strategically equivalent to bidding truthfully in a truthful mechanism. Okay? That's my end result. So, and that's an ex post Nash in a sequential truthful mechanism. So it doesn't matter what the agent knows. But it does matter that they believe that things are sort of lined up right. So this is a great question to talk about maybe offline. Okay, so this is my mechanism. You see what dashboards are. I'm now going to give you, I told you I'm going to progressively make my dashboards more and more complicated. So my first simplest dashboard is just the last stage inferred values dashboard. So in stage S, what I'm going to do is look at the inferred values I had from the last stage. I'm then going to say, well, what if I plug these inferred values into the last stage's allocation rule, but I change the player I's value in that to get an allocation rule, which I'll call Y. And then I convert that into bid space by the single agent construction for every player to get a bid allocation rule, which is my dashboard. Okay, so I just look at what we were doing last stage, and I give them the bid allocation rule that corresponds to that. So here's the static analysis, which David predicted. Following the dashboard converges to a Nash equilibrium, and in fact, in two rounds, right? If we all follow the dashboard 2 stages in a row, then in the second round, the dashboard's right, and it was best response to do what the dashboard says. Cool, that's the least interesting result here. However, I like it because it says that in steady state, there's nothing to do. Okay, so now the problem is dealing with changes in the environment, maybe the allocation rule's changing, or bidders show up and leave. That's going to be, so we might have to do some additional work to get things to be good then, but in steady state, we essentially do nothing.
Jason, are there other agreements?
Just for reference, if we were to run a sequential truthful mechanism, there are all kinds of other equilibrium than playing truthfully in a sequential truthful mechanism.
Yeah, but you can tell people.
Excuse me?
You can advise people to be truthful. That's,
Yeah, I can also advise people to follow the dashboard. So I really care about the sequential properties, not the single round properties of Nash. And so I'm going to be stuck with all of the funny equilibrium that the sequential truthful mechanism has. I can't get rid of them. Cool. So that's my static analysis. I now want to generalize, come up with a better dashboard for settings where the environment could be changing, but a player has the same persistent value in every round. Okay. So this is just the last winning stage dashboard. And here's what I do. For every agent, the dashboard I offer them is coming from the allocation rule that they received the last time they won. The theorem is that following the dashboard with a static value converges to the right average outcome in the sequential truthful mechanism, if we were running a sequential truthful mechanism for this agent. Okay, the proof is simple and cute. Okay, so fix a value v that you might have. Consider successive winning stages. So I'm going to index my stages that I won by k. So sk minus 1 was the last time I run, and sk is this time I won the auction. And here's the thing. The bid you give me in sk is responding for this value to the dashboard from sk minus 1, which is the correct dashboard for sk minus 1. So the amount you make now when you win is the right amount to have paid me in the last round that you won. Okay? In other words, the bid strategy in this round is equal to the correct bid strategy for the last round. Cool. If I sum the total payments over all rounds, this imbalance across, I just paid you at the wrong time. I paid you the right amount, but the wrong time. Okay? And everything cancels except for the first and last round. And the first and last round difference of bids is at most v. Okay? Because the bids difference of any two bids in a mechanism where I have value v can be at most difference of v. So even though my dashboard has you pay the wrong amount at the time you win, the next time you pay me the right amount. So it's almost like a deferred payment mechanism, essentially. You pay me the right amount next time. Okay, and we're playing in a repeated game, so I don't care if you pay me the right amount this time or next time. You're going to pay me the right amount eventually, and so why worry about it? This requires my value to be the same in every round. Otherwise, the payment might not be the right amount next time if my value changed. Okay, so the last thing I'm going to do is try to come up with a dashboard that works okay when my value is changing. Okay, and I already gave you the idea for this. Basically, the intuition is, well, if my allocation rule is changing across rounds, then my payments might be incorrect when I publish the wrong dashboard. Let's keep track of how incorrect my payments are from the wrong dashboard. Add that to a balance, and let's make sure that I collect that balance eventually in the future. Okay, this is actually not very complicated. There are some pretty subtle things you do want to do to get it right. In particular, if I'm collecting balance in the future, I want to really make sure I don't overshoot. And so if I owed you $1, it'd be horrible if next round we overshot and now you owe me $10. Right? And then that could oscillate out of control and just result with really high imbalance of payments. Okay. Cool. So we have inferred value v hat. We implemented allocation x. We have an actual bid c. We had a desired bid b. And we really wish c was equal to b. That would have been the right payments for this round if c was b when I charge you b when you win. Right? But we didn't get that. And so there's a payment residual, which is the difference in these two. That's sort of how much wrong we had, how much the payments were wrong. Okay? So I'm just going to, every round, add the payment residual to a balance, adjust the dashboard payments by putting this into the P0 term, the payment you pay with value 0. That doesn't quite work, as I said, but we can approximate that, and you can see the paper for the details on how to approximate that. Okay. Cool. So the details, I think I want to skip given the time because it's not all that exciting. The main lemmas that go into analyzing this dashboard are proving that the additional payment residual from every round is bounded between minus v and v, that we resolve a balance, but we never overshoot. So the amount we resolve is between ELT and some eta less than 1, and the total balance. And that unresolved payment residual from round K after K winning stages sort of exponentially or decreases. Cool. I want to, as I predicted, I don't have time to talk about the single call mechanisms, so see the paper for that. And my discussion is fairly straightforward. Online markets can have bad equilibria. The sequential dashboard mechanism can implement any outcome of any sequential truthful mechanism. A nice thing is that we have to do sort of complicated rebalancing to fix things only when there's changes in the environment. Okay, so sort of dashboards naturally rebalance themselves otherwise. Some directions. I think there are interesting approaches for making this practical. One thing I especially think are interesting is that if you can make your dashboard estimates better, that's going to make a better user experience. But the theory that we did is going to work even if the dashboard's wrong. So we have a theoretical method for resolving balance that's going to work for any dashboard you come up with, and you can use any heuristics you want to show a dashboard. And this rebalancing approach automatically corrects for mistakes that you made and gives you the good incentives. I think this area of designing a theory for non-truthful mechanisms is incredibly important. It's been overlooked in the literature for almost the entirety of the literature on mechanism design, and I think we need to think about it, especially with these applications to online markets. I think there's a technical thing that is quite interesting, which is designing mechanisms based on bit inversion, which we haven't seen very much of, but I think it's a really powerful idea that when we put bit inversion into mechanism design, we can actually do some things we weren't able to do before. Cool, thank you very much.
So, do bidders trust the dashboard? Wasn't there a paper, a couple years ago about Zillow doing having a sort of recommendation tool?
Yeah.
And it turned out that a lot of the real estate agents, I think, were kind of,
Yeah. Yeah.
And it turned out that a lot of them didn't actually trust the recommendation tool.
Yeah. So I think trust is a super important issue, and I think that the fact that the thing we say is actually, the payments are going to be, if you have a static value, your payments are right the next time for the last time, as I showed you. But maybe that's not good enough for the experience of the agents in the mechanism. They're like, that was way off from what you said was going to happen, and I don't believe what's going on at all. And now I'm sort of very reluctant to follow any strategy. Yeah, I think that's a big issue. And so I would lump that into sort of practical approaches for dashboards, and I think that resolving that, making the user experience better, is a key practical issue.
Just to follow up on that question, so they don't actually have to follow what's in the dashboard, or do they actually have to optimize taking the dashboard at face value? Like there's a compliance problem, so maybe they don't completely ignore the dashboard, but so it does influence their behavior.
Yeah. So here's the thing. In every round, I assume their value is in best response to the dashboard, and we produce the efficient outcome. And in the long run, so the theorem that I didn't state but I said many times, equivalence to the sequential truthful mechanism, where following the dashboard corresponds to bidding truthfully. What does that mean? If you don't follow the dashboard in some round, you've bid some other value. It's like, in the long run, you were bidding in a truthful mechanism, you bid the wrong value, which means you lost. Okay, so.
But in the Zillow case, it seems like they didn't still learn, right?
That's correct. Yeah. And I think in what I propose here, I think there's definitely an opportunity for them not to learn. And one of the reasons why is that the payment is delayed, and it's hard to realize that, oh, these things are balancing, and so I attribute the payment here to this. So that it's confusing. And so that's why I say that I think there are practical challenges in getting there, and sort of how you explain this, and how you,
you don't have to give the payment like, or charge the payment at the moment of allocation in these high frequency auctions, you can give a like monthly bill, and then the monthly bill will be approximately correct.
Yeah, and so potentially aggregating across many payments would make it seem much more accurate, because it is. It's like only the first and last one are wrong, and then if you aggregate over the month, as Nicole says, then it would be pretty close to right on. Yeah.
How does this change if you have like discounting value of time? So given that you're going to win stochastically going forward?
I think it would change because I'm charging you the wrong amount now and charging you the right amount later, and so I'm charging you more now or less later, and I think it would change.
But do you see that as a fundamental theoretical problem, or do you see that just as...
No, because I don't think that the rates people discount are higher frequency than the amount they're allocated. As long as your next time, as long as you're patient enough for your next allocation, then I don't think it makes a difference for real applications.
So if I had a static pairs bid mechanism I wanted to implement, in principle I could teach people using a dashboard to play the ex post Nash equilibrium by breaking it up into a sequence, right? So in some sense this could be seen as like a learning tool for static settings.
Yeah, so you could take your item and allocate it into fractional items and actually allocate each one, and you should maybe get to what you want very quickly. I haven't thought about that very carefully.
Great. Thank you. Thanks, Jason. And we have a lunch break.